for the combination of the, hey everyone, it's a pleasure to introduce our last speaker of the series, jointly coordinated by the Dreams Seminar and the Citrus People and Robots Initiative. Now, this speaker is someone I've admired for many years, and I've also grown to know as a friend. He has an amazing track record in history, some of which you hopefully were able to read online. But just a couple of the highlights. He grew up in Texas. He went on to New Mexico for a double E degree, and then did his PhD at Stanford University.
Oh, you could say it.
I can say it.
The last time I was at Berkeley, the guy got
it. You know, up here, we're pretty comfortable with it, but it's okay. Anyway, but nevertheless, he decided to wind up here at Berkeley, which is the sign of wisdom. So he has this incredible history of doing amazing things in computer vision.
My wife works in the building.
Yes.
That's why I'm here. Yeah.
Allison Gopnik. So he invented the HSV color transform and the alpha channel. And if you've done any work in graphics or computer vision, you know what those are. He had the first full color paint program. He has 2 Technical Academy Awards and started the graphics lab, first original member of the computer graphics lab at NY in New York. He was the first director of computer graphics at Lucasfilm and was co-founder of Pixar, which was later sold to Disney, and also Altamira, which was sold to Microsoft. He was also, one of his great claims to fame was that he was the one who hired John Lasseter to Pixar, who is obviously one of the greats of all time. So we thank you for that. He's done so many other things. He was involved with the Human Genome Project. He's a member of the National Academy, the AAAS. He's even got artwork in the Museum of Modern Art. And this book, I know that he's worked on for a number of years. It's really a labor of love. 10 years, because I remember him talking about this maybe 8 years ago or so and saying, I'm working on this book. And then every time I would see him, I'd say, how's that book? And it came out, here it is. It came out during the pandemic. And it's the biography of the Pixel. And it's absolutely wonderful. It's a bunch, it also includes such a history of things you never knew. And it's really eye-opening. And it's a huge pleasure to welcome today, Alfie Ray Smith.
Thanks. Thanks, Ken. Yeah, I just live a few blocks away from here, so this is not hard to do. And it's great to be in public. I hope it's okay. This is my first time out, by the way, in like 2 years or something, so I'm pretty excited about that. Okay. Okay, so like Ken said, I started out 10 years ago to write this book. Not knowing it was going to take 10 years. I thought I would just sit down and write it from my memory. It's not a history of Pixar, although there's history of Pixar in there. It's not a history of computer graphics, although there's a history of computer graphics in there. It really is the story of the Pixel and how it's changed the modern media world. And one of the motivations, there's several motivations. One was I was kind of surprised at how little I knew about my own career. Like, I've been in computer graphics for 50 years, but I couldn't tell you who did the first of anything. I mean, some things, but did Ivan Sutherland really start it all? Turns out not at all. But I didn't know that. I couldn't tell you my own field. Who made the first movies? I couldn't tell you. And I solved it in the book. Who made the first color? Who had the first color pixels? I didn't know. I figured it out for this book and so forth. Who built the first computer? I didn't know, so I worked it out. It's in this book. So I'll just give you a little sampling of some of the things I discovered along the way. And where AI kind of fits in vaguely in the sense that I started in AI. I came to Stanford University in 1965. They had this new department there called CS, and they had this new subject called AI. And I was fascinated by that. I had stumbled over Marvin Minsky's Steps Towards Artificial Intelligence article, and I said, that's for me, and came to Stanford to learn it. I kind of dropped out of it after a while, but I've been following it all along, nevertheless. Okay. another motivation for the book is that nobody seems to know what a pixel is. If you're like me, I have millions, maybe billions of pixels in this little device right here. You can't see one. You can't see them. That's one of my lessons. You can't see pixels. And when you ask people what they are, you get all kinds of cockamamie answers. I went out and asked Google what pixels look like or what they were, and I got, and then I said, Google, I put in the word pixel, and then images, clicked on images. And this is just a sampling of what Google said pixels were. Pixels are not little squares. I'm telling you right now, they never have been. So kind of one of the curious things I want to talk, or the book talks about, is where did this myth come from? Why is everybody so comfortable with it? And I think I have a strong answer that I'll share later, but I think one of the answers is that everybody, or at least until recently, people thought computers were linear, rigid, mechanical, numeric, boring. So the pictures that they made would have to be linear, mechanical, boring, and raise the little squares. It just was consistent with what everybody believed. And it just so happens that today this event happened. Have you heard about this? Coca-Cola just announced today, 2 May, their new drink, Coca-Cola Bite, complete with pixelated logo. And if you look down at the bottom, it's pixel flavored. I can't wait. I can't wait to see. I can't wait to taste it, to see what pixels taste like. Anyhow, that's today. And it just furthers this myth of little squares. And maybe even voxels down here. Voxels aren't little cubes either. Okay, so let's do a real quick theory of pixels, just so we're all talking about the same thing. It all goes back to Fourier at about, in the French Revolution, about, let's call it 1800 plus or minus. This is a picture of the guy. This is probably a more accurate picture of him. Came up with the idea. So the first chapter is about Fourier, because I didn't know about Fourier. Everybody here has heard of him, but do you know his story? It's a pretty good story. Did you know he almost got his head cut off in the French Revolution? He was in prison waiting for his turn at the guillotine because he became a foul of the Robespierre. Luckily, Robespierre lost his head, freeing our guy, Fourier, who then ran off with his new buddy, Napoleon Bonaparte, to Egypt. He was with the group who discovered the Rosetta Stone, and on and on. His story is really a good one. I'm not going to elaborate it here. It's chapter 1. What he did, and why we talk about him, is he came up with this idea that the world is all music. It's the way I put it. We know that music is a sum of frequencies, of sound waves of different frequencies and different amplitudes. And there's a picture of some of his, I don't even call them sine waves. I eschew all mathematics in this book. They're sine waves, but I just call them one-dimensional Fourier waves. They look like this. They vary by how fast they wiggle and how fast they crest, and that's it. They're very regular, and his astonishing theory is that you can add those together to get any sound. Like, here's the word yes. See the high frequency, how time is going to the right. Not only sound, not only music, but any sound. And yes is an example of that. Not only that, but you can go into 2 dimensions and represent 2-dimensional things like pictures with 2-dimensional waves. To get a 2-dimensional wave, you just take these 1-dimensional waves, extrude them out of the plane to get corrugations. And you'll notice that the edge of these corrugations is a 1-dimensional Fourier wave. In fact, any cross-section is a 1-dimensional Fourier wave. And if you kind of zoom up and look down on a corrugation, it looks like that. They look like that. It's just a sample. The astonishing theorem is you can add those together, highly regular, to get irregular things like pictures of your kid. This happens to be my kid, back when Return of the Jedi was still called Revenge of the Jedi. Or you can get a picture of, like this silly picture of Napoleon. I make a big deal out of tyrants in this book. This guy was Fourier's tyrant. First he was his buddy, then he sent him off to Grenoble and wouldn't let him into Paris. He put him in exile. Fourier was not allowed to come back into Paris until this guy got sent off to St. Helena for his final exile. At which point, well, did you know he came up with the greenhouse effect? Fourier did. And he championed Germain. Sophie Germain was one of the great early female mathematicians. All right, but I bring up Fourier theory because I really want to talk about sampling theory, the fabulous sampling theorem, which is what all the modern media world is based on. It's what pixels are about. And one of my surprises was that no, Claude Shannon did not prove the sampling theorem. He never even claimed he did. I couldn't believe it. I'm sitting here reading the famous paper he wrote. He doesn't claim. He just said, it's in the air. And I think one of the reasons he didn't give this guy credit is because this guy was a Russian commie. His name was Vladimir Kotelnikov. Did you know about him? Yeah. And he comes from a long line. That's chapter 2, a fabulous story. He comes from a long line of mathematicians all the way back to one of the 6 students of Euler. So he's got quite a pedigree. And he just seemed to come up with the sampling theory on his own, and he published it in this paper in 1933. I can't read Russian, but I could read the math, and the math is exactly the way I use the sampling theorem, complete with bandpass and low-pass versions today. I mentioned, okay, so there's a big debate about this, which I outline in the book. And by the way, 300 more pages online for the cognoscenti like yourselves, where I bang out the battles between all the claimants. So England has a claimant named Whittaker. And I actually give Whittaker a big presence in one of my later chapters. He didn't do the bandpass, but he did pretty much everything else. He also did it from the reverse point of view than we use. But I call him a father of interpolation because that was his point of view. And he was definitely there. It's the same theorem. You can use the same program to do both spline interpolation and pixel reconstruction. It's pretty amazing. To me, it's one of the pretty things in this book. We show you the same theory works in both places, both in reconstruction and in construction. Unfortunately, I got to take that guy's picture out of there. The more I learn, the worse it gets. But that picture shows Kotelnikov in 2003 in the Kremlin being knighted, or whatever it is in Russian, by the other Vladimir. You can see that Kotelnikov is sporting all the merit badges of the Soviet Union. He lived through the entire thing, the World War I, the Revolution, World War II, the Cold War, everything. And he managed to stay out of the Gulag because he had a protectress. His protectress, see, the story is juicy. His protectress was a woman named Valeria Gorostova. And the reason she could keep him out of the Gulag was her husband was Malenkov. Malenkov was the bloody guy, just as bloody as Stalin, who took over just after Stalin. You know, responsible for millions of deaths. That was his protectress. So I didn't know any Soviet history until I worked on that chapter, and I was just blown away by what I learned. And out of it comes the sampling theorem, and all I really want you to remember is that shape right there. It's a sink, but I don't use those words, right? I call it a spreader, and you'll see why in a moment. So what is this? What is the great sampling theorem about which I'm so full of praise? Well, let's do the one-dimensional case first. I'll run through this real fast. You probably already know it, but just to be sure. Okay. What Kotelnikov said, or Whittaker, or whoever you want to give first credit to, let's start with one dimension. So think of this as a sound, a sound amplitude versus time to the right. one-dimensional case. What Kotelnikov said was, if you place points regularly along that curve, and I'll tell you what the rate is in a moment, that's key, then you can throw away the infinity of points between these are samples. You can throw away the infinity of points between the samples and hold on to your socks, not lose anything. What? It's not an approximation, it's exact. Digital is not an approximation of analog. It's a beautiful, beautiful result and not obvious at all. All right, so what is this sampling rate that you've got to exceed? Well, remember, Fourier told us that any signal like the one that we started with is a sum of Fourier waves. He said, find the Fourier wave in the sum that's the highest frequency. And I contend is, in this case, it's that one. And then sample at twice that rate, or slightly greater actually, than twice that rate. If you do, then you can throw away the infinity of points between. It looks like you're getting something for nothing. But here's how it works. 10 years later on another planet, on the other side of this one, you can start with your set of samples. And if you want to hear the sound that it corresponds to, the second half of the theorem tells you how to get there. It doesn't say that is the sound there, that just represents the sound. The way you get it back is, remember that shape? You spread, in my terms, each sample, add the results up, and that gives you back the original. Now there's one catch here. This spreader, the ideal spreader, is infinitely wide. Those ripples go out forever in both directions. And we can't use infinitely wide things in our world. So what we do is we replace it, with a good approximation. This is a pretty good one. All right. Then you spread each sample, and that's why I'm showing here. You put a copy of the spreader at each sample and adjust its height so it's the height of the sample. And then you add up the results and you get that bold curve at the top, which is the original sound. Almost. Remember, we approximated the spreader, the ideal spreader with a finite width. So we lost a little bit there, but not very much. This is really close to the original signal. So the infinity is stored in the spreader. The infinities that we thought we got rid of are actually in the spreader. Really clever repackaging of infinity is what this theorem is. Okay, but I personally am more interested in the two-dimensional case. So let's jump. So in this case, the set of samples looks more like a bed of nails because it's two-dimensional. And we call those samples pixels. That's the definition. And the spreader looks like this, which if you guillotine this thing right down the center, you can see that its cross-section is the one-dimensional spreader. So here's a picture of one pixel, one sample, being spread by that spreader, which is close to ideal. Notice that several things about what I've said so far. A pixel only exists at a point. You can't see it. I've also not used a little square anywhere. It's definitely not a little square. If you're going to insist on giving a shape to a pixel, then it's the shape of that spreader, it's not a point. Okay, so why? And that brings up one of the great misconceptions of our times. So we've got millions or billions of pixels. I do on my cell phone, so do you. When I say, show me that image, the power of the screaming fast power of computers today displays the image almost instantaneously. It seems instantaneous. It's actually the reconstruction I just explained being done really fast. And what you see are these little glowing spots that overlap, rows and columns of them. those are not pixels. They're display elements. The pixels you can't see. They're back behind. They're in the files. Okay. So what you see, so what the great confusion of our time is to confuse those little glowing spots, which are analog and overlap, with very digital and spiky pixels. There are completely different kinds of things. So confusing them is just an error. You can also see why people don't know what pixels are. I've invoked Fourier theory and sampling theory in order to get here, right? But no little squares ever. Oh yeah, so where does that myth of pixelation come from? I gave you one notion, was that people think that computers are rectangular and linear and rigid, and therefore pixelation seems to fit people's notion of what computer pictures must be, even though they're surrounded by evidence that that's not so. Like, right, well, that's not a very good example, but pictures of us on Zoom are all pixel mediated, and they aren't little squares. You haven't seen little squares, but you think you have, because of this feature called zoom. So I made this picture with Photoshop of 14 pixels. They're actually looking at 14 spread pixels because you can see them. And they're tiny, right? So you want to see what they, so we use Photoshop's zoom in feature to show us what that picture looks like up close. Let's say I've zoomed by 32. I can't quite remember what I actually used here. And you get that picture. Little squares. Therefore, there must have been little squares originally. It's a lie, folks. It's a total lie. It's a cheap and dirty trick. All that Zoom does, and almost every app has a zoom. All that Zoom does is replace each pixel with a square array, in this case, 32 by 32 pixels of copies of the original pixel. What does a square array look like? It looks like a square, but it's not a picture of the pixel up close. We can use the sampling theorem, however, correctly to show us what that really looks like when you zoom. Also with Photoshop, it's called image size, where you resize, you reconstruct the image and resize it and then take a look at it. That's what it looks like up close. You know what you're looking at are those little mountains I showed you earlier from above. And they overlap and they're soft and they're not squares and so forth. All right, enough of that. Now I'm going to jump to computers. What do you think the first computer is, just out of curiosity? Anybody want to volunteer? I'll just say it's not ENIAC. ENIAC. So part of the terms you have to define terms, it turns out, in order to get these histories right. And a fast calculator made out of vacuum tubes in the size of a room is not a computer. It's not a computer unless it's programmable and fast. The whole idea of computers, so let's step back to Alan Turing, the guy on the left. He's one of the few sole stars, where a single guy actually did do it all. He invented computation, gave it its name, and was one of the first to go off and say, let's make this go fast by building what we now call computers to make it go fast. By the way, I designed a hardware version of a universal Turing machine, and I got a stack of them here if anybody wants one. Okay, that could compute Toy Story, but it would probably take the lifetime of the universe to do it. So Turing's great idea is not just computation, it's the universal stored program computer. He invented the stored program computer, by the way, which is, by the way, what we mean by the word computer. That's why ENIAC is not a computer, it didn't have a stored program. Colossus, which was even earlier in Great Britain, also is not a computer, it didn't. You could rewire them with cables and things to make them execute a different algorithm, but they weren't programmable. So I came up, another early leader, one of the few guys in the world who's smart enough to know what Alan Turing had actually done is this guy, sitting on a mule, ass backwards on the Grand Canyon wearing a business suit. That's Johnny von Neumann, who's a real character, but he was smart enough to know exactly what Turing had done, and they both set out to build hardware computers that make the notion of computation go fast. If it doesn't go fast, it's worthless. All right, so I came up with this scheme. These stories turn out to be a lot more complex than a single hero, and everything comes from that single hero. Here's the flow chart, or the genealogy of the history of computers. And sure enough, Alan Turing's own computable numbers is at the top. It was key. And Alan Turing and John von Neumann are at the top. You'll start noticing down below them, both of them tried to build computers. Alan Turing's failed for a variety of reasons that I put in the book. And you can see across the middle there, Pilot Ace, Baby, EDSAC, ENIAC Plus, Zephyr, Whirlwind, some of the first computers. They came really fast in the late 40s, early 50s. And the reason they're here, I'm going to talk about just two of them. This is really all we have time for. Baby, University of Manchester, which I contend was the first computer, and the Whirlwind computer at MIT, which is kind of, if you look down below, Whirlwind, it says modern computer graphics descends from there. That's why I have it in there. But the reason Baby's in there is because the first pixels were on Baby. Not only was it the first computer, by the way, I should back up just a little bit. There's high contention right now that what I'm calling ENIAC Plus beat out Baby by a couple of weeks. ENIAC Plus. So John von Neumann looked at the ENIAC and said, look, if you change the hardware a little bit, it becomes programmable. And then it becomes a serious machine. Those changes were made. And the historians are fighting it out right now about, I mean, basically, where do you call, when's it done? If you got half the instruction set implemented, is that done? If it runs a program, is it done then? You can get ENIAC Plus to beat out Baby depending on how many instructions you can say are done. So I just called it a tie. And this happened after I started writing the book. So I had to kind of change everything up to be sure I give credit to both of them. Baby, however, I pursue completely because ENIAC didn't have pixels. ENIAC Plus didn't have pixels, but Baby did. So I visited Baby, 2013 in Manchester, England. This is Baby's display. And when I showed up there, this was on its display. And the word Pixar was scrolling to the right. The first computer, probably, maybe, had pixels and it could animate. Who knew? So the story of the pixels go all the way back to the beginning of computers. That's why I study computers so thoroughly here. Then I started looking around. I found the actual first pixels. This is somebody actually took photographs of what I call first light. And this is it. Tom Kilburn took it. He was one of the engineers who built Baby and came up with a visible way of storing bits on the face of a CRT. It was the first good memory system for a digital computer. That's why they won the race. No little squares, right? The very first picture has no little squares. There never have been any squares. Then I looked a little further and I found the first interactive game. So that first picture was 1947. This first game that I found was also at Manchester, 1951. It's interactive, game of checkers. And then the second one I found, I'm not sure it's the second one, but the second one that got pictures of, but they actually stopped and made pictures at the time of tic-tac-toe at Cambridge, also interactive. So 1952 or 3. So there were pictures made of pixels that were interactive and you could animate even, but let's step forward. I'm going to step forward to the Whirlwind. I spent a wonderful day in the photographic archives of the Whirlwind, which weren't at MIT where I expected to find it, but at a MITRE Corporations, which is a secretive place that you have to get clearances for to get into in, I think it's Bedford, Mass, or someplace like that, with the curator. And she and I had a ball all day long. She kept wheeling out boxes and boxes of photos. They weren't shy about making photographs, making pictures. There's a whole thing in my book about how people thought pictures were frivolous and a waste of the computational power. They would not admit to me that they even made a picture because it was forbidden fruit. But not of the Whirlwind. They made pictures gleefully, and lots of them. And there are a lot of firsts there. I'm not going to go through them. except for that bottom right. Hello, Mr. Murrow, I believe, was the first animation. It's 1951. It's made of pixels. It was showed on the Edward R. Murrow show, See It Now. And it's validated. All right. Something I'm not going to spend much time on today is the history of movies and animation. But just to suffice it to say that, as usual, I didn't know who made the first movies, and it wasn't until I worked out the genealogy of movies that I discovered who did and who didn't, and who stabbed who in the back, and so forth. And it's a nasty story. Just give you a feeling of it. The guy on the right here is Edward Muybridge, not Edward Muybridge, like I hear people saying all the time. His real name was Teddy Muggeridge from Kingston-on-Thames. And he changed his name. He had 8 aliases that I've been able to discover in his life. And only the last one did he take on at age 52, where he started spelling his name E-A-D-W-E-A-R-D, because that was the spelling of Edward, the King Edward's name on the coronation stone in his birth town, Kingston-on-Thames. So it's just Edward Muybridge. It's not Edward Muybridge. He turned out to be a real showman, and that's about all. But his tyrants, I have a lot of interplay between creators and tyrants in this book. His tyrant was Leland Stanford. Leland Stanford, the tyrant's role is frequently to make a creator's idea possible, but not understanding what he's doing. Like Leland Stanford sold the rights to Muybridge's technique to Muybridge for $1. He didn't have any idea what Muybridge was up to. But there's lawsuits between the two, and it was really nasty. Okay. Stanford won, by the way. Muybridge did not invent the movies. I kind of lay that to waste in the book. A lot of people think Edison, in his Napoleonic pose, invented the movies. Nah, he didn't. He thought it was a good idea that there be something like movies. So he assigned the job to this guy, whom I bet you've not heard of, William Kennedy Laurie Dixon, who, if there's any one guy who should get credit for inventing the movies, it's probably that guy. The Lumiere Brothers, I cover the Lumiere Brothers too. 1895, there were all kinds of people that had movies. The Lumiere Brothers weren't the first. Edison wasn't the first. They were not. And they did not love each other. Like the French love to tell you that the Lumiere brothers loved each other. And they came up with this wonderful system that was both a camera and a projector. I've actually held one of their devices. They are lovely. The curator of the Cinémathèque Française was my contact and source of my historical information. So the French, so my genealogical chart is the Yanks versus the Franks. I cover the French very carefully in the book. I'm not going to show you today, but there was all kinds of stealing of ideas and people stabbing people in the back, and it was really ugly. So the Lumiere brothers stabbed each other in the back. But the nice tailored creation myth has in France that the Lumiere brothers did it all. No, there were actually a bunch of contenders in 1895. That was the year. I've got the flow chart showing you all the different contenders. It wasn't, okay, that's another whole thing I go off on. And then there's the history of animation, which I didn't understand at all, much to my surprise. So I just put up this one picture. It's of Walt Disney and Ub Iwerks. Ub, the original name of the company was Iwerks Disney, but Disney has written Iwerks out of the story pretty much. And in fact, I tried to get permission to publish this picture and Disney lawyers wouldn't let me. I said, well, Pixar is worth billions of dollars to your company. It didn't matter. I called Disney a tyrant. So they went. He basically stole credit from Ub invented Mickey Mouse and animated Steamboat Willie, who was the director of the first Mickey Mouse feature. Okay, he's the guy. I'm going to rush right through this. This is my first attempt at 3D animation. Put this down. This was at New York Tech in the late 70s. We had a program. We could not do 3D really for all practical purposes. Computers were still too slow. But I had I modeled one of my hands with cylinders and spheres. That's all we could do was ellipsoids of various kinds. And then I got the hand and I replicated it and mirrored it. And I said, okay, now what can I do with these two hands? Why don't I make them clap? Well, I did that, and it's boring as hell. I mean, if you just look at what a clap really is, it's really boring. So at that point, I appealed to what I knew about animation. These techniques that the old animators had come up with, squash and stretch and anticipation and exaggeration, and I applied them to this model. I bent the hands all the way back, impossibly far back, and I slung them together, and the tips went out and exploded and withdrew. And when I played this thing back in real time, it was juicy and lovely and fun to watch. It made you feel good. And it made me think I was an animator, which I was not. It took me a while to learn that. But it taught me to respect what these old animators with no notion of sampling theory or any of that had come up with. And these are my hands again, before I discovered computer graphics completely. In the early 70s, I drew this picture with rapidograph, India ink, and French curves. And it got used as the cover of the proceedings of the Foundations of Computer Science for 38 years. Why I show it here is because it's not Renaissance perspective. It's a really weird perspective. I had to appeal to Escher in order to solve the problems that I solved in this drawing. Which brings me to the subject I kind of featured in my blurb, what I call the Central Dogma. But before I elucidate the Central Dogma, let me say a few words about the history of computer graphics. It's often, I kind of thought, having worked for years with a lot of graduates of the University of Utah, that Ivan Sutherland started it all with Sketchpad. 1962 at MIT, 1963. No, not quite that. It's not quite how it worked. It was actually these three guys who were all classmates at MIT. Ivan did Sketchpad, but it was only two-dimensional, much to my dismay. The guy who gave us the first interactive three-dimensional, in a way I have to qualify about dozens of pages, was the guy in the middle whom you probably never heard of, Tim Johnson, still alive, never been honored. Wrote Sketchpad 3, not version 3, but the 3D version of Sketchpad. And it had perspective. It showed pictures in perspective. For his perspective solution, he took the math from the third guy in the picture, whose name is Larry Roberts. Now, Larry has never been honored by the computer graphics community, but he has been highly honored because of his role in being one of the founding fathers of the internet. I talk all about it. That's where he came up with his solution for perspective. I do too. I appeal to it. He's got, to me, what's important in that thesis is his solution of perspective. He figured it out. And he also came up with a 4x4 matrix and the homogeneous coordinate and all that, which is there are several early contenders who invented perspective in computer graphics, but the one that we use is his. Okay. So I call these guys the triumvirate of computer graphics. It's not just Ivan, it's all three of these guys. No, and you see his problem? He looks just like Ivan. If you go out on the internet and type in Sketchpad and images, nearly over the majority of pictures you'll get back are not of Ivan Sutherland on Sketchpad, although they'll all say that. They are really of Tim Johnson on Sketchpad 3. And I called him. I said, "What about that?" He said, "Well, what can I do? Yeah. he ended up being an architecture prof at MIT. Yeah, so he's I said, well, I'm going to try to turn that around with my book. You need, that's just not right. Ivan was a little angry with me because I demoted him a little bit, but you can't demote Ivan. He's a real powerhouse. So I said, but Ivan, you didn't do 3D. It took 3 more years before he did the first head-mounted display, in which he did invoke, what I'm calling the central dogma of computer graphics, which is we will model objects using Euclidean geometry in the memory of a computer, and we will render that onto a display using Renaissance perspective. Now, the reason I call this as a dogma is because there's nothing about a computer that requires those 2 restrictions. And I actually was kind of surprised that nobody ever said that before. So I wrote it down, and it helped me clarify many problems I've had in the decades of my career, where I ended up arguing with people and we didn't know what we were arguing about. This turns out to be it. Paint programs don't honor the central dogma, for example. But a lot of things, so, for example, I would get up and give a lot of talks in the early days, and people would say, Alvy, is your goal to simulate reality? I went, no. I want to make art. I grew up painting oils and acrylics on canvas. I want to make art. And, but it turns out a lot of my colleagues were into simulating reality. So they look at me kind of puzzled, like, what? Okay. This captures it, I think. I'm going to come back to this in a moment. There's another restriction required too. All right, here's the flow chart for early computer graphics. Here's the Triumvirate. You'll notice the Whirlwind box with the arrow to it. That's where this flow chart connects to the preceding one. So you can see these flow charts. The only way you can actually show these histories is by showing all the threads that are at work and how the people interact. Again, one guy did it all, just doesn't work. The simple narrative does not work when you're given the history of high technology. So I don't have anywhere near enough time to talk about all the interesting stories on this slide, but I would like to point out these Nazis, the guys saved from the Nazis. In particular, my boss, when I graduated from Stanford, I took a job at NYU with this guy, Herbert Freeman. Turns out to be one of the earliest guys in computer graphics. Was saved from the Nazis by Albert Einstein. I didn't even know that until I wrote the book. The other guy I want to point out, and the story is just as astonishing, is Marceli Wine. Marceli Wine and Nestor Burtnick wrote the first computer interpolating animation program. It's 2-dimensional. So I spent a day talking to him, and he told me the most amazing story. He was in the Krakow ghetto when he was a child. His dad got hauled off to Auschwitz, and he threw Marceli off to a woman in the crowd as he was being hauled off to Auschwitz. And she raised him as a Christian. And then the father was saved from Auschwitz because he was a master tailor, and he was saved by Schindler by being number 5 on Schindler's list. Okay. Try to put stories like that in there to make it not such a terrible read. Well, of course, he's one of the big players. I just don't. You want me to talk about him now? Oh, yeah. Well, okay. So do you see the word ARPA under Robert Taylor's name, Larry Roberts' name, and Ivan Sutherland's name? These 3 guys at separate times got hauled off to ARPA, the IPTO section of ARPA, and they handed out money that basically kicked off the world of computer graphics. One of the places that they funded was Dave Evans at Berkeley. And then Dave Evans, after Ivan finished his tenure at MIT and Harvard, I think, Dave Evans said, come join me in Salt Lake. And they started the famous computer science department at Salt Lake. Dave Evans being a devout Mormon. And the first machine they built was called the LDS-1, not for Latter-day Saints, but for line drawing system. Okay. I mean, these stories go on and on and on. Okay. What? No, I'm pretty sure not. He was another guy, Bertram was another guy saved from the Nazis by the Kinder Transport Program. And well, Jim Bland studied under him, if you know Jim Bland. Okay. Like I said, all these things are tied together in all kinds of interesting ways that I can't possibly relate to you today. All right, so far I've been talking to you about, let me back this up, about the early days, what I call epic one of computer history. Baby is there. This is when computers got bigger as they got more powerful. And then something miraculous happened in 1965. Moore's Law got announced, and that's the beginning of what I call epic 2, where computers got smaller as they got more powerful. Moore's Law is usually stated in this not very transparent way, doubling of density of components on an integrated circuit chip every 18 months or so. I put that in the base 10, and it comes out to be this more memorable form. Everything good about computers gets 10 times better every 5 years. I actually use the term order of magnitude because we puny human beings can't think more than one order of magnitude. We just max out. That's happened every 5 years since 1965. And that's what this Moore's Law curve, I can't overexpress the importance of Moore's Law. It's an engineering feat of astonishing consequence. My entire life and career is based on it. Yours is too, because it's still going. And we don't know where it's going because we don't understand what an order of magnitude means until we get there. We can look back and say, oh yeah, of course, but you can't. Another way I like to say it is if you can predict by an order of magnitude, you can probably become a billionaire. All right, so factor was 1 in 1965 when Gordon Moore announced this law. It's not a law really. And I made my first computer graphic that year, plus or minus a year. At about 1 million X is when Toy Story came out. Today, we're beyond 100 billion. Moore's Law factor of 100 billion. And we're soon to hit 1 trillion. We don't know how to think. We just have to live our lives and get there to see what that means. And I'd say the current state of AI is highly dependent on the fact that we've got this astonishing supernova of computing power at our fingertips now, and it's going to get more and more powerful. All right, one back. Well, another thing about Moore's Law is color pixels. Color came to graphics with Moore's Law. Moore's Law is the first. So when I went to look for the first color pixels, I found them. This chart's basically this chart's it's more and more complex, and it ends up with Pixar, DreamWorks, and Blue Sky at the bottom, and all the different streams that work together to get there. I'm going to just cut through that and show you the first color pixels. I finally found them. They were on a simulator for the Lunar Excursion Module for NASA. This is them. They were 6-bit, and I met the 2 engineers who did it. They're in their 80s now, live in Salt Lake. Rod Rougelot and Bob Schumacher, wonderful old gentlemen. They're older than me. And we spent 7 hours, delicious hours together, reconstructing this moment and saying, that's when it happened. And it happened to be the summer of love, but that was just a coincidence. So, what? Yeah. Well, it certainly affected my life, I can tell you. So, I thought, so I'm leaping ahead pretty fast here. This is the paint program at Xerox PARC. where I suddenly, my friend Dick Shelp had built this program. He said, hey, he knew I was a painter. He said, come look what I'm doing. And I went, painting and graphic and computers, that's me. And I got myself hired on at Xerox Park. Dick kept telling me these aren't the first color pixels, but he couldn't tell me who. So that's why I had to research it for the book. But Xerox fired me. They decided to go black and white. Decided not to do color. I went, okay, bye. And leapt to this place on Long Island. This is one of the buildings on the campus of New York Institute of Technology. It's got to be one of the most amazing places on the planet. It's owned and run by this guy, Alexander Schur, Uncle Alex, we called him. The mansion you're looking at is where the video was done. Through the woods, a few, quarter mile was another mansion where computer graphics got done. And that's where I met Ed Catmull and where the group now known as Pixar started. It's at this fabulous place, run by our first of several patrons, very wealthy man, who basically bought us everything we asked for without understanding what it was he was paying for. He eventually lost it all. We had three patrons, George Lucas and Steve Jobs being the next two, who became billionaires on our backs. But this guy lost it all. He was too soon. One of the first things he did was bought us the first full color 24-bit pixels in the world. He bought the second 8-bit frame buffer in the world, picture memory, from Evans and Sutherland, this new product they had made, for $80,000, $1970. And then he came to me one night and he said, "What? We're in head of the world, aren't we?" And I said, "Yeah, we are. We got the best graphics lab that there is." He said, "How do we stay there?" I said, "Well, if you buy me 2 more of these 8-bit guys, I can gang them together to get a 24-bit memory. And then we'll have 16 million colors instead of only 200. And then we can do astonishing things." And I didn't know whether he understood me or not. He was a pretty weird guy. And several weeks later, he stumbles back into the lab and he says, "I bought you 5 more of those 8-bit thingies so you'd have 2 of those 24-bit thingies." So the first 24-bit frame buffer cost him $200,000. In today's money, that's well over $1 million. And then he did it again. So he spent about $2 million on my say-so. It's only now when I look back, I see how astonishing that was that he did this. Anyhow, we went crazy making art, just showing the world what you could do with full color, which is some of everything. And that's where we had the idea for why don't we make the first computer-generated movie? We were working by the way, at this campus with a old-fashioned cell animation crew of 100 people making a terrible movie called Tubby the Tuba. It was awful. And I met Ed Schwiller there, and this is where I made a piece that's in the Museum of Modern Art. I'm gonna skip over that. Okay, we finally figured out Uncle Alex really didn't have it as a producer of a movie for us. And we leapt to join George Lucas. And that's where I got the break on the big screen. Our team did Star Trek II, the Genesis demo on Star Trek II. And then a couple of years later, I'd hired John Lasseter and we made Andre and Wally-B. But not only were we showing off that we could do character animation, not just animation, but that we had solved motion blur. This was a key technical solution before computer animation could be on the big screen. That's 4 successive frames. Just to show you our solution, what the solution was. Smears in the direction of motion, and you can tell by the size of the smear how fast things move. And it made all the difference in the world. Also that year, 1984, as you can tell by the numbers on the pool balls, one of our resident geniuses, Tom Porter, made this picture, which we had to tell people was not real. And it demonstrated that we had solved all the problems that needed to be solved to do renderings for the big screen. And this is where I reintroduced the Central Dogma, because we've added one more line to it. We will simulate Newtonian physics. So everything we do will be inside this symphotic form that I call the Central Dogma, Euclidean geometry, Newtonian physics, Renaissance perspective. It sounds like a really narrow space, but of course, every 3D movie that's out there was made inside this creative space. But what I want to do is tell the world, especially the artists of the world, is you don't have to make pictures inside the Central Dogma. Break out of that and show us what else is out there. I'll skip over this. George and Marcia Lucas got divorced, and suddenly he lost half his fortune. I went to Ed and said, Ed Catmull, my partner, said, let's start a company. And this is two nerds talking to each other. We went to Larkspur Landing over in Marin and bought How to Start Company books. And the amazing thing is that we did it. We went through 45 funding opportunities before we finally landed Steve Jobs. 5 horrible years with him, but he kept us alive. You know, tyrants have this role of making things happen even when they don't mean to. Where 45 groups turned us down financially, he didn't. And he was able to make a billionaire of himself out of that. But the result was, at the end of that 5 years, Moore's Law had done its trick. Disney knocked on our door and said, okay, guys, let's make that movie you always wanted to make. And they basically, we'll pay for it. So they saved Jobs' reputation, and they got us to our goal. So DreamWorks did Ants, and Blue Sky did Ice Age at all about the same time, which is the millennium, 2000, plus or minus. And I say that's the year, and that's what I'm celebrating with this book, that the great digital convergence happened, when all old analog media types disappeared and were replaced by the bit, pixel in case of. So now it's true that nearly all pictures in the world are made of pixels. In fact, there are so many of them that nearly all pictures that have ever existed are made of pixels. Part of what I call digital light. All right, so basically 2000 is the end of my book, French Revolution to 2000. But, you know, 20 years have elapsed since 2000. That's a factor of 10,000 Moore's Law. So everything good about computers has got 10,000 times better since then. So that's where I just kind of wanted to touch you guys. This is the famous zebra horse paper. An old buddy of mine, a pixel packing buddy of mine, saw me at Cambridge University, where Allison and I were on her sabbatical at King's College, Turing's college. And he handed me this paper, says, Alvy, we don't have to program anymore. I said, what are you talking about? He said, look at this paper. And I looked at this and I said, how does that work? He says, I don't even think that's a well-defined problem. What's a horse? What's a zebra? What? He says, we don't know. That's what I'm trying to tell you. The GAN just figures it out. And you let me use these pictures, thank you, in the book. And of course, it does go wrong, so I will show this guy once. I just want to sort of the last sort of a question to you, because I really don't know, is what I always thought that when we got to an intelligent machine, I didn't know how it works. And that with this paper, I said, oh, maybe not. I think that's what Turing's paper was really about. Why the halting problem is unsolvable. If a computer can compute on its program, then there is no way to know what it's going to do. So I think what we're seeing here, and you can tell me whether right or wrong, is that these nets there is no separation of program space and data space from the computer itself, and that therefore it must be computing on its own program. And once you enter into that space, that we puny human beings, once again, cannot possibly understand what it is that's happening. You just sit back and enjoy it. Anyhow, I'll stop there.
take maybe one question is,
Okay, and don't forget I have Turing
oh,
machines
Turing
up here.
machines up there for everyone who needs one. Okay, quick.
I have recently been reading a bit about Charles Babbage and Ada Lovelace, and I have a quote that will start my question and goes very much along your initial thought about computer being able to work not only on discrete quantities. And it's like many persons who are not conversant with mathematical studies imagine that because the business of Babbage analytical engine is to give results in numerical notation, the nature of the process must consequently be arithmetical and numerical, rather than algebraic and analytical. This is an error. The engine can run and combine numerical quantities exactly as if they were letters or any other general symbol. And in fact, it might bring out results in algebraic notation where provisions were made accordingly, which made me think a lot about your idea of not working on discrete quantities. But my question is, where would you place Babbage analytical engine?
Well, I put them in an intellectual heritage, but I don't give them primacy. They did not come up with the full notion of computation. Turing did that with its unsolvability.
But they were programmable and they were fast. It was programmable and fast, wasn't it?
It only did arithmetic.
Okay.
And they did not have the notion of stored program computability down. They just didn't have it. They certainly contributed to the zeitgeist of the subject. But I claim that Turing was the first guy that just nailed it in an astonishing leap of creativity. Even his own teacher couldn't hardly believe this toy solved one of the most difficult mathematical problems they had at the time. I spent quite a bit of time shooting down myths of computers in the book. They don't have to be electronic. They don't have to be based on myths. They're definitely not about arithmetic. They're about patterns, and they are about process. He nailed the idea of careful process. Now, one of the careful processes that we do is arithmetic. So yeah, it makes sense that we'd use it for arithmetic, but any careful process is what Turing mastered. And we did not know the profundity of that notion until he wrote on computable numbers.